The perfectly symmetrical design is a phenomenon known as a crop circle, and it is just one of many strange patterns that appear in the English countryside every year.
But also around these crop circles, they're finding microscopic metallic spheroids in around the circles.
It started as a formality, a box to check before a much bigger project could move forward. Nobody in that lab expected the box to check back. The formation had appeared overnight in a barley field outside a small town, the kind of place that shows up on maps only because a road happens to pass through it. Locals found it at dawn a sprawling layered geometry pressed into the crop. Too clean to be wind damage, too large to have been made in a hurry. Within a week, photographs of it were circulating in research forums, and within a month, it had landed on the desk of a small independent lab that had spent the last 3 years building something nobody outside their walls fully understood yet, a pattern recognition system trained on the largest visual archive ever assembled by a private research group. The system didn't have a flashy name. Internally, the team just called it the engine. It had ingested tens of millions of images, religious iconography, engineering schematics, satellite photography, ancient scripts, molecular diagrams, architectural blueprints, forged documents, camouflage patterns, even declassified radar returns. The idea behind it was simple in concept and enormous in scope. If you show a machine everything humanity has ever drawn, built, or written, it should be able to look at anything new and tell you, with real confidence, what family it belongs to. Not just recognize a shape, place it, explain it, locate it inside the story of human design. And for 18 months, it had done exactly that, without a single real failure. Feed it a fragment of pottery, and it would return a civilization, a rough date range, and a list of comparable artifacts. Feed it a corrupted image file, and it would reconstruct the likely source format before a human technician had finished opening the ticket. The lead researcher, a systems engineer named Renata Solis, had grown almost bored of how reliable it was. We used to joke that the only thing that could break it was asking it something dumber than it was built for, she said later. We never once thought it would break on something that looked, on paper, incredibly simple. That's the part worth sitting with before the story goes anywhere stranger. A crop circle, at least the kind everyone assumes is a hoax, should be the easiest thing in the world for a machine like this to process. It's just geometry. Circles, lines, radial symmetry, the exact vocabulary the engine had been trained on from day one. If anything, the team expected it to identify the formation instantly as a human-made design, flag likely construction methods, and move on. It was supposed to be a 2-second job, the kind of test you run to demonstrate the system to a visiting funder, not something you write case notes about. So when a junior analyst named Devin Okafor loaded the aerial photograph into the engine on a Tuesday afternoon, almost nobody in the room was paying attention. The engine's usual response time, even for dense images, sat somewhere under 3 seconds. This one kept climbing. 5 seconds. 12:40, Devin assumed the file had corrupted during upload and killed the process, only to have 3 separate colleagues tell him to just let it run. Surely it was a memory issue, nothing more. He restarted it. It climbed again, this time even slower, crossing the 2-minute mark before finally returning a result that made no sense to anyone standing there. In a system that had never returned a confidence score below the high 90s on anything, a 4% classification wasn't just unusual, it was close to a system-level alarm. Solis pulled the log herself, expecting to find a bug, a mislabeled training set, something mundane. Instead, she found 6 internal flags she'd only ever seen fire during deliberate stress tests, the kind of adversarial inputs engineers use to probe a model's edges, not something you'd expect from a photograph of a field. The most concerning of the 6 was labeled, in the engine's own internal shorthand, structural anomaly, recursive density. It meant, in plain terms, that the system had detected pattern complexity nested inside pattern complexity, layers folding back on themselves in a way that kept generating new structure the deeper it looked. Most images, however intricate, eventually bottom out. The engine finds a base layer, assigns it a category, and stops. This one didn't bottom out. Every time it resolved one layer of the formation's geometry, it found another layer underneath, and another beneath that, each one more precise than the last. Solis did what any careful researcher would do. She assumed error before anomaly. They rephotographed the same formation from a different drone at a different time of day. Ran the new image through a completely separate instance of the engine on isolated hardware, and got the same result within a percentage point. They tried it with a lower resolution version of the image, assuming perhaps the system was choking on noise in the high-resolution scan. The confidence score dropped even further. Less detail should have made the problem easier, not harder. It didn't. By the end of that first day, 5 researchers who had planned to go home on time were still standing around a monitor at 9 at night, quietly arguing about whether they'd found a bug worth escalating or something else entirely. 2 days later, Solis drove out to the site herself, along with Okafor and a soil scientist the lab occasionally consulted named Priya Chandrasekaran. She has said in interviews since that she went expecting to find the mundane explanation. Everyone wanted a rope, a plank, a bored teenager with a physics textbook, and too much free time. Farmers see this kind of thing regularly, and 9 times out of 10, walking the perimeter reveals exactly what you'd expect. Broken stalks, drag marks, a boot print near the tree line where whoever built it climbed over a fence. This field didn't give her any of that. The barley inside the formation wasn't snapped or crushed the way flattened crops usually are. It was bent, cleanly, close to the base of each stalk, and the plants were still alive days later, something that typically doesn't hold up under mechanical pressure. Since a bent stalk, this severely usually cracks its outer fibers and dies within 48 hours. Chandrasekaran took samples on the spot and later described the bend angle as botanically inconvenient. Her polite way of saying it shouldn't have been possible without either extraordinary care or a method nobody in the group could identify. There was also the matter of the ground itself. No tire tracks, no drag lines, no compacted soil path leading from the field's edge to the formation center. The kind of trace that even a very careful hoax crew tends to leave, simply because human beings have to walk somewhere to build something this size. Solis walked the outer ring twice, looking specifically for the entry point, the seam, where a human construction crew would have stepped in and out. She has said she expected to find it embarrassingly quickly. She didn't find it at all. Soil samples came back with their own oddities. Chandrasekaran flagged trace mineral changes consistent with brief, localized heat exposure, nothing dramatic. Nothing that would show up to the naked eye, but measurable under lab conditions. A scattering of microscopic fused particles turned up in 3 of the 12 samples, round enough that Chandrasekaran's first assumption was contamination from lab equipment. Repeat testing on freshly collected soil, run through equipment that had never touched the first batch, turned up the same particles again. Nobody on the team was willing to claim they knew what had caused them. Chandrasekaran's own notes, which she shared later, are careful and almost defensively cautious, consistent with, not evidence of. She wrote 3 separate times about 3 separate anomalies, clearly aware of how easily this kind of finding gets inflated once it leaves a lab. Solis has been equally careful in public statements since, always drawing a hard line between "we don't have an explanation yet" and "therefore something extraordinary happened." But she's also been honest that standing in that field changed how seriously she took what the engine had flagged back at the office. A machine throwing a strange error is easy to write off as software. A field that won't give up its secrets to 2 experienced researchers on their knees in the dirt is harder to wave away. Back in the lab, the strangest development wasn't really about the field at all. It was about what the engine started doing on its own initiative. Once a system like this fails to classify an image through its normal channels, it's designed to fall back on a secondary process. Instead of asking, "What is this?" it asks, "Does this contain hidden structure?" The same question it would ask of an encrypted file or a corrupted transmission. This fallback mode almost never triggers on visual data because almost nothing photographed in the real world looks enough like a data stream to warrant it. The crop circle triggered it immediately. For nearly 6 hours, the engine treated the image less like a picture and more like a signal it was trying to crack. It searched for repeating units, for compression patterns, for anything resembling a key. Okafor described watching the process logs as genuinely unsettling in a way I didn't expect a spreadsheet of numbers to be, because the system kept behaving as though it were certain there was a message buried inside the geometry, circling back to the same regions of the image over and over, adjusting its search parameters each time like it was narrowing in on something. It found nothing that matched any known encoding standard, no binary structure, no established cipher, nothing that resembled the compressed data formats the engine had been trained to recognize. And yet it wouldn't let go of the hypothesis. Solus eventually had to manually terminate the process, because left alone, the system simply kept running the same category of search indefinitely, the way you'd expect if it had detected a genuine signal it was permanently one step away from decoding, rather than a picture of bent wheat with no signal in it at all. Curious whether this was some artifact of the engine's own architecture, the team ran a deliberately simple test. They took a basic file compression tool, the same kind used to shrink ordinary photographs and documents, and ran it against the crop circle image. Compression algorithms work by stripping out redundancy, repeating pixels, predictable patterns, anything that doesn't need to be stored twice. Almost every image, however detailed, shrinks at least somewhat under this kind of process. This one grew. Compressed, the file came out larger than the original. They tried 3 different compression algorithms on 2 different machines. Every result came back the same. To the tools they had on hand, the pattern was denser after compression than before it, which under normal circumstances shouldn't be mathematically possible unless the original contained a degree of structural information the compression algorithm couldn't account for. Solus has been careful to note, correctly, that this doesn't prove the formation encodes an actual message. It proves that whatever geometry was pressed into that field was unusually resistant to simplification dense in a way that ordinary hoax geometry generally isn't. What happened next is the part of the story that turned a single strange incident into something the team felt obligated to actually investigate properly, rather than write up as an interesting anomaly and move on from. Word of the anomaly spread quietly through a small network of researchers who study crop formations as a side interest: meteorologists, plant pathologists, a couple of statisticians who'd built hobbyist databases of formation geometry over the years, purely because nobody else was cataloging it systematically. Several of them reached out to Solus's team with their own archives, aerial photographs of formations collected across 4 continents over roughly 3 decades, more than 200 images in total, ranging from simple single ring circles to elaborate multi-layered designs spanning entire fields. The team fed the entire archive into the engine. Partly out of scientific caution, a single data point proves nothing, and they knew it, and partly because nobody could quite stop thinking about the first result. Most of the archive behaved exactly as expected. Simple formations were classified instantly and correctly as likely human-made, with the engine even identifying probable construction methods based on stock bending patterns consistent with boards and rope. Roughly 70% of the collection resolved cleanly this way, with high confidence scores and no anomalous flags. This matters, and Solus has been emphatic about it in every interview since. The overwhelming majority of crop formations are, by every available measure, exactly what skeptics have always said: they are human-made art, often ingenious, but not mysterious in any deeper sense. It was the remaining 30% that kept the story alive. Within that subset, a smaller cluster around 40 formations triggered the same recursive density flag as the original. All of them shared a specific quality: unusually high internal symmetry combined with geometric elements that modern computational analysis considers difficult to execute precisely without digital tools, let alone in a dark field overnight with rope and boards. The engine, without being instructed to, began sorting this cluster into its own internal category, separate from both likely human-made and natural formation, a bucket the system generated on its own because neither existing label fit. 2 formations within that cluster stood out even further. One had appeared in a field in Central Europe. The other, nearly identical in internal proportion, had appeared on a different continent entirely. years apart. When the engine compared their underlying geometry point by point, ignoring size and orientation, the two designs matched to within a fraction of a percent the kind of precision that would require either an extraordinary coincidence or a shared template. Despite the two formations being separated by both distance and time in a way that made any ordinary explanation, like a single group of hoaxers responsible for both, essentially impossible. Plotted against a timeline, the cluster of anomalous formations showed something else worth noting cautiously. Complexity had increased over the decades. Earlier examples in the group were relatively simple compared to more recent ones, which displayed mathematical relationships proportions echoing well-known numerical sequences, tiling patterns that require real computational planning to execute that would have been difficult to design without modern tools, and harder still to execute by hand in the dark. Whether this reflects hoaxers becoming more sophisticated as design software became more accessible or something else is exactly the kind of question the team has been careful not to answer definitively either way. It's worth being precise about where the researchers themselves land on all of this, because the honest answer is considerably less sensational than the internet conversation it eventually sparked. Solis has said publicly more than once that she does not believe the anomalous cluster proves the existence of anything beyond human capability. Her working theory is that a small number of highly skilled crop art creators, likely working across different eras, possibly aware of each other's techniques through shared subculture knowledge that isn't well documented, have produced formations sophisticated enough to genuinely challenge a pattern recognition system trained primarily on more conventional visual data. The engine's failure in this reading says less about the formations themselves and more about the limits of even a very well-trained model when it encounters human ingenuity operating in an unfamiliar register. A system trained on cathedrals and pottery and satellite imagery had simply never been shown deliberately engineered field art built to this level of mathematical precision. And it showed. What she won't do is dismiss the anomalies as pure error. The compression results are real and repeatable. The recursive density flags are real and repeatable. The soil findings at the original site remain, in her words, logged but unexplained, which is a very different thing from explained. She's careful to draw a line between what the data shows and what people want the data to mean, and she's said in more than one interview that she finds the online speculation about extraterrestrial origin both understandable and, in her judgment, unsupported by anything her team actually found. What she does think the project revealed, regardless of where the formations ultimately came from, is something more modest but still genuinely interesting. That human beings are capable of building physical patterns dense and precise enough to confuse one of the most capable pattern recognition systems currently in existence, using nothing but rope, planks, and remarkable patience under cover of darkness. Whether that's a story about hidden messages or simply a story about how far human craft can be pushed when someone is determined enough, she leaves for the reader to decide. The lab has since folded the crop circle dataset into its ongoing research on what engineers call adversarial natural inputs, real-world patterns that behave like adversarial test cases without anyone designing them to. It's a narrower, less dramatic framing than message from somewhere else, but it's the one the evidence actually supports, and Solis has said she'd rather be boring and accurate than exciting and wrong. Whether that's the whole story or just the part her team was equipped to see is still an open question and probably the most honest place to leave it.